So in this video we're going to have a look at how we can work out what the pressure is in a liquid, and then once we've done that we're going to move on and have a look at Archimedes' principle and see how we can work out how buoyant an object is, whether it will float or sink, and how we would calculate the size of the upthrust due to being submerged into a liquid, or in that case indeed a gas as well, so into a fluid. Okay, so if we take this body of liquid that we've got here in this rectangle or cuboid, I'm just going to make the drawing look a little bit more three-dimensional, like that. And like with normal pressure, we can say that the pressure is the force per unit of area. Okay, so what we need to look at here is what is the, let's set this up. We've got at the bottom here an area, let's call that A, and we've got a depth of liquid or a height of liquid, and let's call that H. Now the force acting on the area at the bottom will of course be the weight of the liquid. So what we've got to do is we've got to work out what weight of liquid we've got. So the weight is equal to mg, and from this what we have to do is we've got to now work out what's the mass of the liquid, because we would know what g is. So the mass of the liquid we're going to work out from the density, and we know that the density is the mass divided through by the volume. So if we've got a liquid of known density, we can work out the mass. So the mass from this is going to equal rho v. Now we know the mass, we can put this into here to work out the weight. So that will give us a weight of rho v, which is the mass, multiplied by g, and that will tell us the weight of the liquid. Now what we can now do is we can work out what the volume of the liquid is, because the volume is going to be the area multiplied by the height. So I can rewrite my weight as being W equals rho H A divided by G. Now if we then substitute this and put this into working out the pressure, because of the force, so if we substitute the weight in for the force and then divide through by the area, we will end up getting that the pressure is equal to rho H A G divided through by A, and hopefully you can see that the A's are going to cancel, and that will tell me that my pressure is equal to rho G A. Now what's interesting about this particular formula here is, although we've got a pressure, we can see that the only things that the pressure inside the liquid depends on is the density of the liquid, the gravitational field strength, and the height or the depth of the liquid. So the deeper the liquid, the higher the pressure we get, and it doesn't depend on the area at all, because that's cancelled out. Now we're going to have a look at how much upthrust we get when we submerge a body into a liquid. So if we take a look at this body that we've got submerged into our liquid, we've got the liquid having a density here of rho, and what we're going to work out is we are going to have a force acting on the top area of our body, and we're also going to have a force acting on the bottom area of our body. So if we just work out what those two forces will be, so at the top surface we know that the pressure is going to equal rho G H, and therefore the force, because the pressure is the force over the area, the force is going to equal the pressure multiplied by the area. So what we would get here is we can now say that our force is going to equal our pressure, rho g h, and we'll multiply that by the area we've got where the pressure is acting, so multiplying it by A. Now if we look at the bottom surface here, exactly the same thing, only the only difference we've got is that not only is it at height h, it's also got an extra height, which is the width or the thickness of the object that's being submerged. So if we have a look at that, so here we're going to see now that then the force underneath is going to equal rho g, but now the height is going to be h plus our extra bit of depth x multiplied by A, and that will tell us the force at the bottom. I'm going to multiply out the bracket, so that's going to give us that F is equal to rho g h plus rho g x. Sorry, I've forgotten to multiply by the A, and that's also multiplied by the A. Let's make my plus sign a bit more obvious. Right, let's just write that out again. Sorry about that. Okay, so we're going to have rho g a h plus rho g a x. Okay, so this is the force at the top, this is the force acting on the object at the bottom, so let's just put a couple of little subscripts in, and now therefore the resultant force will be these two added together. The force at the bottom is going to be pushing up and the force at the top is going to be pushing down, so if I add these two forces together I would subtract them, so I've got, let's take the force at the bottom minus the force at the top because they're acting in opposite direction, and that will equal my upthrust. So let's substitute in. So we've got rho g a h plus rho g a x minus rho g a h, because that's the force at the top, and then that just leaves me, so that part there will cancel with that part there, and that tells me that my upthrust is equal to rho g a x. As I'm sure some of you might be able to work out, the area multiplied by the x here gives me the volume of my object. So just to finish this off, I can say that the upthrust caused by the liquid is equal to the density of the liquid multiplied by g multiplied by the volume. And what we can see here, this here is what we would call Archimedes' principle. So if we just put in a new page, we'll state what Archimedes' principle is. So as we just saw, the magnitude of the upthrust due to the liquid is equal to the density times by the gravitational field strength multiplied by the volume. So the upthrust of the object is equal to the weight of the, so this term here is the weight of the liquid that has been displaced by the object, and that will tell us the upthrust. So we'll just write that out in words. So Archimedes' principle states that the upthrust exerted on a body immersed in a fluid, whether fully or partially submerged, is equal to the weight of the fluid that the body displaces. Just in this final section then, we're going to have a look and see whether a body will float or whether it will sink. So if a body is submerged in the liquid and it's fully displacing it, we've got two forces acting on this body. We will have the weight of the body that's being submerged, and we will have another force, the upthrust, acting in the opposite direction. Now, the body will sink if the weight is greater than the upthrust, and here the body would, let's put that in as sink, and if the body floats, when it's fully submerged, then the weight will be less than the upthrust, so it gets pushed back up towards the surface. Now if we have a look at this body, we can say that we know that the mass of it is going to equal, so the mass of the body, m, is going to equal the density of the object multiplied by the volume, and therefore the weight, mg, is going to equal the density of the object multiplied by the volume multiplied by g. And now we saw earlier is that the upthrust is going to equal the density of the liquid multiplied by g multiplied by the volume of the water that's being displaced, which is going to equal, sorry, the liquid that's being displaced, assuming it's in water, which will equal the volume of the object that's inside our liquid. Now, if we take the floating situation, we can say, let's do the floating situation. What we would say is if the density of the object times V and G is less than the upthrust, which is the density of the liquid, G times V. Here you can see that they've both got a Vg term which will cancel out, so an object will float if the density of the object is less than the density of the liquid, and the reverse is true for something that sinks, where if the density of the object is greater than the density of the liquid, then the object will sink.